You've heard it said that the world works in mysterious ways, but rarely has that seemed truer than right now. The forces of nature are the absolute cornerstones of reality as we know it, and so much of physics is calculated with these four fundamental qualities in mind. Together, they're what guides and shapes most of everything in our existence. But now, there's potentially something new on the scene, and it could push us to rethink everything we thought we knew before. This is Unveiled, and today we're answering the extraordinary question, did we just discover a new force of nature?
Are you a fiend for facts? Are you constantly curious? Then why not subscribe to Unveiled for more clips like this one and ring the bell for more fascinating content?
What are the four fundamental forces, otherwise known as the forces of nature? First, there's probably the most famous of all, gravity. Then there's electromagnetism. Then the two nuclear forces, categorized as strong and weak. In short, these correspond to four physical interactions that are irreducible. They cannot be scaled back and described as anything more basic than what they already are, and they are therefore present throughout the universe, providing a kind of framework for how things happen, which is why the findings from a recent study are promising to shake science to its core. The study in question, the muon G-2 experiment, has taken place at the Fermi National Accelerator Laboratory in Illinois, otherwise known as the Fermi Lab, and it centers on muons, a particular type of elementary subatomic particle. Muons are typically described as being similar to electrons, only that they're about 200 times more massive. They can prove difficult to study because they decay so rapidly into electrons, but up until recently, they were generally expected to follow the standard model of particle physics with its four forces of nature. That is, they weren't expected to do anything weird or interact weirdly at a fundamental level. However, when a team of scientists between the years 2017 and 2020 beamed muons around the 50-foot diameter Fermilab accelerator at close to the speed of light, they noticed that something was up with the way they wobbled. They were moving, or wobbling, at a faster rate than the standard model would have predicted for them, which has led researchers to suggest that some other unknown force or possibly particle must be working on them. With muons, it would seem, we require something more than just gravity, electromagnetism, and/or weak and strong nuclear forces to make sense of what we're seeing. The established rulebook of physics doesn't quite provide us with all we want to know. A variation in the wobble rate of a subatomic particle may sound like a small thing, and physically speaking, of course, it is, but for scientists around the world, this one observation could have dramatic and exciting consequences. While it by no means disproves the standard model, it does indicate that the standard model misses something. At this stage, researchers are increasingly confident that what's been detected at Fermilab isn't an error or a random fluctuation. One major reason for this confidence is that this isn't the first time that the experiment has been conducted. Back in 2001, a similar study concluded with similar results at Brookhaven National Laboratory in Long Island, New York. Over the years since, the equipment used at Brookhaven has been moved thousands of miles across the United States to Fermilab, where it's now updated and improved, and still producing the same irregular wobble rate for muons. Scientists aren't yet confident enough to label the findings as a clear-cut discovery, but over the next few years, there will be many more experiments held to generate more data and glean more information. At this stage, there's a gap between what the standard model of particle physics says should happen and what's actually happening. So, physicists need to plug that gap. Ultimately, what does all of this mean for life as we know it? To return to the Fermilab results, they potentially suggest one of two things. Either there's another unknown particle buzzing around the place and affecting muons, or there's another unknown force. Either way, it's the unknown that has gotten everyone so excited. Physicists are now almost sure that there is something fundamental that they can't be sure about. And the challenge today is to adapt our standard model so that it can make sense of this new information. It could be a challenge that takes years, even decades, to meet. Importantly, while it may in the past have seemed like outlandish science fiction to propose a new force of nature, it's increasingly not so. The Fermilab experiment has, at this moment, no direct link to dark matter and dark energy, but the study of those two particular scientific enigmas has informed much of the debate until now. The hypothetical quality of dark energy that's come to be known as quintessence, for instance, is frequently cited as a possible fifth force of nature. Regardless, with dark matter and dark energy, we're already accepting that there's so much about reality that we can't really explain. That there's so much, perhaps, that isn't contained by only gravity, electromagnetism, weak nuclear force, and strong nuclear force. And in trying to understand it all, there have been other times when the idea of a fifth force or a new particle has been floated. The X-17 particle, for example, was first theorized in 2015 and remains a wholly hypothetical subatomic particle. Nevertheless, it's championed by one Attila Krasznahorkai of Hungary's Institute for Nuclear Research. He and his team claims to have discovered it whilst running an experiment aiming to detect dark matter. The X-17 particle is said to be 34 times heavier than an electron, and would therefore represent something of a midway point between an electron and a muon. A major difference between the X-17 and the irregularity detected by Fermilab, however, is that the X-17 hasn't, so far, been independently detected again. The Fermilab results, meanwhile, are supportive of those obtained by Brookhaven 20 years beforehand and are therefore more widely accepted. Perhaps then, the strangely wobbling muons at Fermilab will serve to bring even the thorny issues of dark matter and dark energy a little bit more into the light. On the other hand, perhaps this potential discovery will have other consequences in completely different fields. It's difficult to predict the wider impact this almost discovery could have, but right now, we could truly be on the precipice of a new chapter in physics and science history. Interestingly, this wasn't the first time in 2021 that muons made the news. In late March, around 3 weeks before the Fermilab findings were made public, scientists working at the Large Hadron Collider at CERN were raising potentially groundbreaking questions about these subatomic mavericks too. A team at the LHC had combed through a decade's worth of data on how B mesons decay, with B mesons being another specific type of subatomic particle. And they found that there was an apparent discrepancy in the rate in which they decayed into muons. While the standard model suggests that B mesons should produce muons at the same rate as they produce electrons, in reality, according to the LHC readings, they don't. B mesons actually decay into electrons more frequently than they do into muons, and that just doesn't fit within the framework of the standard model. So it seems as though science is really beginning to hone in on the muon mystery. It's only in recent decades that we've been able to deconstruct the world in such detail, thanks in large part to the building of particle accelerators all over the world map. For years, we had a relatively basic understanding of the subatomic realm, where protons, neutrons, and electrons ruled. But gradually, we've compiled an increasingly detailed picture of what actually goes on inside an atom. And findings like those coming out of Fermilab may well deal with the microscopic, but they could end up having a massive impact on our macro existences. Previously on Unveiled, we've taken a deep dive into the late John Barrow's scale of microdimensional mastery. At the top end of it, Barrow predicts an advanced civilization with total knowledge and control of the subatomic world. Quarks, leptons, and yes, even muons are all within its power. Humans are still a long way away from this kind of supreme level, but thanks to the Fermilab Muon G-2 experiment and others like it, we could be about to take a very significant step forward. A step toward redeveloping the standard model of particle physics. A step that could potentially uncover at least part of the mystery of dark matter and dark energy. A step that could show us that even our most fundamental laws could be wrong. And that's why scientists may well have just discovered a new force of nature.
What do you think? Is there anything we missed? Let us know in the comments, check out these other clips from Unveiled, and make sure you subscribe and ring the bell for our latest content.